By now we've gotten into angular motion, moment of inertia, and torque, all kinds of good stuff. So in this problem, we're told that there's a grinding wheel, and it's basically a uniform cylinder with a radius of 8.5 centimeters and a mass of 0.38 kilograms. At first, it wants us to calculate the moment of inertia about its center. Then, the applied torque needed to accelerate it from rest to 1750 RPMs in 5 seconds is what we're supposed to figure out, how much torque is needed to be applied. Now, we do have to take into account that there's some frictional torque involved here, and we know something about that we can infer from the fact that we're told that if it was just spinning by itself at 1500 RPMs and it comes to rest in 55 seconds, we can use that to figure out the frictional torque. So there are a few things to worry about here. Let's have a picture in mind as we go through this. We've got a cylinder, so we're looking at it on end. It has a particular radius. I'll call this R. And it's got a particular mass. I'll call this M. Okay. And I'll go ahead and write what we have. We have the radius is 8.50 centimeters. Let's go ahead and write that as 8.50 times 10 to the minus 2 meters and not worry about our units after this. 0.380 kilograms for the mass, 0.380 kilograms for the mass. I'm going to go ahead and admit something, that we're given these numbers to 3 significant figures. And if you're not careful about keeping an extra digit, perhaps a 4th digit, and then only rounding at the very end, you may be off at that last decimal. That's a mistake that I made. So remember to always keep around extra digits while you calculate and only round at the very end. Okay, so conceptually, it's asking for a few things. Concepts. We have rotational inertia or moment of inertia. Okay, it's asking about torque. It's asking about things spinning around and taking a certain amount of time to spin up or spin down from a certain RPM. So we basically have angular motion or angular kinematics, kinds of things that we'll need. Okay. With torque, we should also, that corresponds to having Newton's second law, the angular version of Newton's second law. So I'll just write this as angular Newton's second law. Okay. Equation-wise, then, if we're going to use this, we're going to have to look up the moment of inertia for a cylinder. That's not something I would make you memorize. The moment of inertia for a cylinder is given by 1/2 times the mass of that object times the radius squared. Remember, it always scales like the mass of the object times the characteristic distance squared. The question is really, usually, what is the number out front? In this case, it's a 1/2. Torque and angular momentum. Torque, the net torque applied to a spinning object, will equal its moment of inertia times its angular acceleration. It's just the angular version of Newton's second law. And we have some angular kinematics to worry about. In particular, in this problem, we have something that's speeding up or slowing down at a constant rate. So what we need to remember is that the angular acceleration depends on the change in the angular velocity divided by the change in time, just the way that linear acceleration depends on the change in linear velocity in time. Okay, so let's do part A, which is just to get the moment of inertia. Really, if you just plug in M and you plug in R, what you should find using this formula is that this is, well, let's just actually just stare at this for a little bit. What kind of number should you get? This is worth doing. I is, okay, 1/2, a mass of 0.38, and a radius of 8.5 times 10 to the minus 2 meters, and we have to square that. So even before you plug in your calculator, what we could kind of do is stare at this and think about the 8.5, that's close to 10. So when I square this, that's going to give me a 10 squared or 100. And then the 0.38 is close to 0.4 divided by 2, that's like 0.2 times the 100, so that's like 20 or so, times 10 to the minus 4. We're expecting to get something that's like 20 or so times 10 to the minus 4, or approximately, 2 times 10 to the minus 3. That's roughly the order of magnitude you expect. If you actually plug it in your calculator, you'll find it's 1.37, so a little bit less, but the times 10 to the negative 3, that is accurate. So I'm going to go ahead and write that 1.37, and in fact, this last digit is 2, that is going to be necessary. 10 to the minus 3, and it has units of kilograms, meters squared. There should be kilograms in there, of course. So that is part A. That's the simple thing. Part B, let's kind of sketch out what we're going to need to figure this out. And let's go ahead and draw in here some things that we might need. However you want to think about which way the torque is being applied and which way the frictional torque goes, it's up to you. In my conventions, I'm going to draw it like this. The torque applied, perhaps it's someone spinning it, or it's a motor trying to spin it this way. This is the applied torque, making it try to speed up this way. Friction is always a pain in the ass, and that torque is going to go in the other direction. So this is the frictional torque. Okay. The net torque, we probably are using the convention in class. We typically make it the counterclockwise minus the clockwise, and so given what I've drawn there, the applied torque minus the frictional torque, that's the net torque. That should be equal to the moment of inertia times the angular acceleration. Let's keep our eyes on what is actually being asked for. They want us to figure out the applied torque necessary to do this speeding up. So we're looking to get the applied torque. Let's perhaps put this up here. We may need to refer back to it later. The applied torque is the moment of inertia times alpha plus the frictional torque. We have the moment of inertia. Good. We need the angular acceleration. Okay, let's worry about that. The angular acceleration involves, it tells us that it starts from rest, goes up to 1750 RPMs in 5 seconds. In other words, change in omega, 1750 revolutions per minute, I'm just going to write that as RPM, divided by 5 seconds. These are terrible units as they stand. Revolutions, minutes, we know that we want things in radians and seconds, and so we're going to have to multiply. If we have things in revolutions, remember to multiply by 2 pi radians for every 1 revolution, and the per minute we have to multiply by 1 minute for every 60 seconds. That should be the conversion factor. When you plug in the numbers, you should find that this is approximately 36.65 radians per second squared. It should be, it's an angular acceleration. Seconds on the bottom, we pick up another factor of seconds, and so seconds squared. Okay, so we have moment of inertia, good. We have angular acceleration, good. But we also need to figure out what is the frictional torque. Okay, so now this is a side journey. The frictional torque, we're supposed to figure out what that would be based on the fact that if it was already spinning, it would slow down from a rate of 1500 RPMs to 0 in 55 seconds. So let's think about this. We have to maybe think about Newton's second law again. In the absence of any applied torque, let's think about what would happen. The thing is spinning. There's a frictional torque. It's the same as the friction when you're applying an applied torque to it. This is I times alpha, let's call it alpha prime. This is the acceleration that it's undergoing as it's just sitting there slowing down. Alpha prime is given by the change in the angular frequency over the change in time to go from, it starts off going at a certain rate, it ends at 0, so it's 0 minus 1500 RPM divided by 55 seconds. You can already see we're going to get a negative acceleration, as we should. If the thing was just rotating by its own and slowing down, the angular acceleration should in fact be negative. So this minus sign will hopefully make sense. We're going to do the same thing, multiply by 2 pi over 1 and multiply by 1 over 60 to get it into radians per second. This should turn out to be minus 2.856 radians per second squared. I keep looking over at my notes. You got to realize I did this, I promise. I just don't want to redo it and screw it up for you. Okay, it's minus. We're almost ready to go because now that we have alpha prime and we have I, that means we have the torque needed, and we can finally plug that in here. So let's see how this works. Now we're ready to go back, and I'm going to switch colors to see, just to hopefully make this more clear. This should look like I alpha plus This is, we wrote this as I alpha prime. Right. Okay, let's actually, let me just back up 1 second and clean this up. Because this is the torque, we're going to get the torque now, minus the torque is equal to I times minus 2.856 radians per second squared, and the minus signs go away. Okay, I think that's the point that I wanted to illustrate to you. Therefore, this is I times 2.856 radians per second squared. Probably make more sense to also put the I times the 36.65 radians per second squared. Those are the right units. And we have I, we've already calculated that. So with everything put together, our final answer is apparently 5.42. It's this last digit that you wouldn't get right if you didn't take everything out to four digits. Times 10 to the minus 2, and the units should be, because we're using torque, newtons times meters, which again is not a joule. We write it as newtons times meters to let other people know that we're talking about torque and not energy.